For decades, quantum mechanics has presented us with a stark choice. According to Bell's theorem, we must either accept spooky action at a distance, instantaneous communication across the universe, or abandon the idea of physical realism entirely. In a standard Bell test schematic, a central source emits signals down two pathways toward distant detectors, Alice and Bob. Because the speed of light is the absolute limit, these stations are placed far enough apart that no signal could travel between them before measurement. The mathematics of Bell's theorem are precise. The problem lies in the physical assumptions beneath the math. Specifically, the assumption that the space between Alice and Bob is empty. This image shows how one field theory models the vacuum, a highly structured, continuous, polarisable medium. We are looking at a 3D simulation of continuous wave geometries, caustic tubes branching. The environment is an interconnected fluid, not a void. If the vacuum is a physical medium, the local speed of light we measure might only govern the visible wave. That leaves room for a different, much faster form of deterministic coordination. Think of this vacuum medium as an elastic fluid in a canal. This fluid simultaneously supports two completely different speeds of wave propagation. First, the transverse sector acts like a slow surface ripple. It carries localized energy forward at the speed of light, what standard physics calls radiation. But beneath the surface, the deep bulk of this fluid medium is nearly incompressible. This creates a secondary, underlying dynamic. If you remove a small volume of water from the system, you cause a sudden drop in hydrostatic pressure. This decompression races through the deep bulk as a straight-line shockwave, completely bypassing the slow dynamics of the surface. In the actual electromagnetic field, this longitudinal bulk wave operates at speeds hundreds of thousands of times faster than the local speed of light. This establishes the physical rule for everything that follows. Localized energy travels slowly across the surface, but changes to the baseline pressure coordinate almost instantaneously through the bulk. To understand how this solves quantum entanglement, we have to rethink the detector itself. Superconducting nanowire detectors do not catch tiny particulate bullets. They accumulate continuous wave energy. We model a single detector pixel as a leaky trough at the canal's waterline. It features an upper threshold lip and a bottom drain pump. To register, waves must deliver water faster than it drains. When breaching the threshold, the trough suddenly drops. That mechanical drop is the physical click of the detector. The accumulated energy is permanently ejected out of the closed canal system. Because fluid is suddenly removed, a high-speed decompression shockwave immediately radiates through the deep bulk. The discrete quantum click is an artifact of threshold engineering, not proof of a particle. And every time that threshold is crossed, the extraction lowers the shared medium's pressure. A real laboratory polarizer is not a single trough. It is a macroscopic physical array containing millions of them side by side. Because it has physical dimensions, the angle of this array relative to an incoming wavefront dictates exactly how fast its individual troughs fill up. With a flush, 0-degree alignment, a wave fills all troughs simultaneously, instantly overwhelming their pumps to fire the entire array. Now angle the array to 45 degrees. The wave washes diagonally. The troughs fill sluggishly, constantly fighting their internal drains. This oblique alignment creates a precarious physical tension. Because the wave is constantly losing water to the pumps, the accumulated energy hovers right at the threshold lip without immediately crossing it. An angled detector acts like a system struggling on the razor's edge. Because it is so close to failure, it becomes highly vulnerable to even the slightest drop in the canal's baseline pressure. To run a Bell test, we place Alice at one end of a canal with a flush array and Bob at the opposite end with a 45-degree array. A central source fires two identical transverse surface waves outward. Alice's flush array is hit squarely. It triggers instantly, extracting energy from the canal. That extraction launches a high-speed decompression wave straight back across the deep bulk toward Bob. Because the bulk wave travels 1,000,000 times faster than the surface ripple, Alice's decompression wave reaches Bob's station, while his own slow surface wave is still washing diagonally across his angled array. The arrival of Alice's decompression wave drops the hydrostatic baseline right underneath Bob's array. The marginal water level in his sluggish troughs falls beneath the lip, his internal pumps take over, and his array fails to fire. Standard physics looks at this correlation and assumes the two photons communicated acausally while in flight. But there was no spooky action at a distance. The Bell inequality is violated because an extractogant on one side deterministically deprives the other side of the threshold margin it needs to fire. It is purely energy conservation in a shared fluid. This mechanical reality exposes the fatal flaw in the mathematics of Bell's theorem. It rests on this factorizability equation, which assumes the hidden variable lambda remains static and independent. But as we've seen, that is physically false. The fast longitudinal channel dynamically updates the shared boundary conditions in real time. Statistical independence is structurally impossible. This does not violate the no signaling theorem, because this ultra-fast channel cannot transmit human information. Alice cannot purposefully modulate this decompression wave to encode a message. It is simply the automatic, deterministic response of a conserved medium adjusting its boundaries. By discarding the illusion of the particle and mapping the continuous fluid mechanics of the vacuum, the defining paradox of quantum mechanics evaporates. Local realism survives. The universe remains entirely physical, entirely deterministic, and perfectly comprehensible.